So here is our question. Bare fists were used in boxing matches in the 1800s, the good old days. How do modern boxing gloves better protect the boxer's brain from injury?
I have never not. Because does it cancel like, oh wait, is force lost due to heat and friction on the ears?
That might play a little bit of a part in it. You're right in terms of force.
What was the answer to number one?
Say that, what was it? That's true. And in terms of what we learned last time for our notes, how is that going to change the amount of force? Because remember, force, in terms of the average force we're experiencing, is change in momentum over change in time. Almost. Nope. We're going to change the time here. Because it's the same amount of momentum that's being exerted here, whether you get hit with a bare fist or whether you get hit with a glove, you're going to have the same amount of overall force like put into you. But it's the amount of time it takes for that force, for that momentum to be imparted, that really makes the big difference here. If you take this time value and you make it bigger and bigger and bigger, the average force is obviously going to go down. If you're just using a bare fist and exerting that change in momentum instantaneously, time goes down and injuries go up. So that's the main difference here. It does not change the momentum, it changes the average force. It changes the amount of time it takes for that momentum to be fully realized. All right, so we're going to continue today. I handed out the sheet that has 1D collisions on it. These are mostly just equations that were also on your regular physics formula sheet. Nice. So let's just go through this quickly, and then we'll do 3 examples, and we'll be out of here until Monday.
I cannot wait for it to be the weekend. I have nothing left.
So, one-dimensional collisions. There are 2 kinds of one-dimensional collisions. There are the kind that go like this, and they bounce off each other. We call those elastic collisions, or bouncy collisions. I do too. So that's listed first here. And you've got the equation for elastic collisions right there. You're just adding up all the momentum at the beginning, setting it equal to all the momentum at the end. Momentum, of course, is mv, so that's where that comes from. Now, for these collisions where you've got bounciness, I didn't get you on either yet. See if you can catch it as good as Sim.
I'm never going to do it.
There we go. That was some finesse right there. Oh, Ben wants one too.
Not based on that concept.
I got number 1 right.
I've never not finished this math test in my entire life.
I said, hey, Mr. Mason, are we going to need to know how to make tangent lines on the test? He said, no, don't worry about that. So I'm the study guide. I crossed all of them out. And then half of the test was making tangents. Half of it.
The thing was, I forgot what tangent meant. Like, I have never had such a, like, I had the biggest brain farts on these tests. Yesterday and today, we had 2 big tests. I had the biggest brain farts ever.
It's interesting. We're going to be talking about tangent at the end of class today.
We talk about brain farts.
The odds of that. Oh, we've been talking about that like the last 3 days. It's kind of been a subliminal thing, but not really. So, for elastic collisions, it's when things bounce off each other. For those particular collisions, kinetic energy is also conserved in addition to momentum, which is why we can use kinetic energy equations with that. If you have any energy that's lost, you can calculate that lost energy just by doing change in kinetic energy. With me so far? Well, anyway, just keep on reading along.
Okay.
If there's any specific place that I lose you, please feel free to call my attention to it. These are equations that we use for bouncy collisions. It's a summary. Underneath that, you've got some pretty fancy equations where we actually combine kinetic energy and momentum equations. And those are things that you might need on 1 or 2 problems on the homework. I gave them to you instead of making you derive them. So you're welcome. Yes?
In my test, can you please white out anywhere it says elastic and change it to bouncy? Otherwise, I won't remember.
If I remember, I will.
Thank you.
Inelastic collisions are the opposite kind. Inelastic collisions are ones that go like this. Here's one object, here's another. They come together when they stick together and they move off together. They don't bounce anymore. For those kinds of collisions, momentum is still conserved, which is good. Otherwise, we won't be able to deal with them. But kinetic energy is not conserved because you're losing energy to vibration. And vibration turns into heat, which loses energy. So we cannot do anything with kinetic energy for those kinds of collisions. That's a summary of this. Questions so far?
Make some pretty good football examples out of
Question,
these.
actual, since I don't know why my brain went here. But, so okay, the stuff bounces. But sometimes when it bounces, it's like, think of like a sticky ball. So it bounces and then it picks something up and then it continues bouncing.
Mm-hmm.
What force would it be 2 different forces? Like the bounce is the one is elastic, but then the inelastic is the thing that's
Right.
affected.
The thing is, when we treat elastic collisions in physics, we have to assume they're perfectly elastic.
I talked with my friends. It's not a day to make fun of me.
I think this is the perfect day because we're all just so out of it today.
Can we do a wave like this, starting here and sending it this way?
Wait, 1, 2, 3.
That was really sad.
And send it back into. There we go.
Yeah.
And we are now set to continue. Okay. So, yeah, we have to treat them as perfectly elastic, which would mean that they're touching the table or the object they're bouncing off of just for a split second. If that's the case, then they aren't losing any energy. Realistically, the ball is going to compress a little bit and transfer some heat into the ground, and then it's going to lose energy and bounce lower. So, let's keep going and do a couple examples. Here's the first one.
She's the way he's trying to keep it together when he looks at me.
We just need like 3.
No. Come like hither.
Draw this. I command it.
I think I need a bigger piece of paper.
Alright. So we've got 3 examples to get through and a half hour to do it. I think we can do that.
Is it still supposed to snow tomorrow?
Yeah.
It's
I'm-
raining now.
I'm thinking we probably won't get our observation in.
What are the odds?
Which just means we'll have a game day.
I think I'll get, because the wedding ends at like 7 or something. So I think I'll get
Okay, sure. If you come late, I'd put my phone number on the Schoology thing in one of the updates, so just feel free to text me if you come in late and I'll let you in.
When I go hunting way up north, in the middle of nowhere, I can see literally every constellation ever, nothing.
Yeah.
Do subscripts and subscripts exist?
Yes. I try to stay away from them, but they do exist.
What is the highest number of shooting stars we've seen in a single night? 12.
Can you explain what the beach
Probably around 8. I don't think I've actually kept track, but that sounds about right.
Oh, gotcha.
Yep. Yeah, just get it all drawn in. I'll go over the picture in short order.
So is this inelastic?
I thought it was word.
That is
So a little bit about this graph and picture. We've got ourselves 2 objects, and you can see that mass 2 is headed to the right with some velocity. It impacts M1, which is a little bit bigger. It's picking on the bigger one. And they stick together after the collision, both moving off with a certain velocity represented by this, like velocity 1 and 2. However you want to write that is fine. So the question is, what is that velocity? And we got to figure that out. I think so too.
We've got a physics teacher, I'm sure they can figure it out.
So,
If we stick with what we know, we won't learn anything.
that's true.
I mean, you could just get really good.
This is a good way to start all the problems in this chapter, if you're able to. Original momentum equals final momentum, because that's always going to be true, regardless of what's happening with your collisions. So, if I wanted to solve this problem, what's there originally? Well, m1 v1 original plus m2 v2 original. That's going to be equal to what? Is it going to be m1 v1 plus m2 v2?
Huh?
Yeah.
So this is my original momentum.
No, wait, is it M1 to MV plus MV on 2?
M1
Close.
plus M2.
Yes, yes. So when we say original equals final, it becomes almost second nature to put the same thing over here, just without the original. But because these two objects are sticking together, you have to make sure you remember on the sheet that I threw somewhere that you have the combined masses, and those times the combined velocity is equal.
Force that, like, yeah?
Yeah, just like the Atwood machine where the forces are going up and down in the force section.
That's what I was going to say. Just think about it.
So if I want to solve for V12, I just got to isolate it.
And that's easy because you already have it isolated somewhat.
Yeah.
Yeah.
And then you could just plug those numbers in.
This math makes sense.
Good.
I'm just going to start writing this stuff on my drug test. Write the tangent line. No, but did you know that F equals M?
Indeed. So these inelastic collisions tend to be relatively straightforward. You're just solving for the combined velocity of both objects after the collision. Where this gets really interesting is when instead of having two objects moving in one dimension, you've got them moving in two dimensions and they collide. Oh yeah.
Nope.
Oh yeah.
Nope.
We're doing that.
Nope.
Yes, we are.
No.
Oh yeah.
Nope. That was.
I'm like the Kool-Aid man, but I'm gonna bust my way into your brain with what's left of this Friday.
I thought you said what's left of it, and I'm like, there ain't any left.
Questions on this first problem here? Okay.
The fact that only five
You see, is he smarter than me? The only thing I didn't finish.
Here's the next one. Write this down, please.
Yeah, I didn't finish the half of it.
I finished it with 1. I spent about 4.
And I definitely did one wrong, and I definitely did two wrong, and I definitely did three wrong, and I definitely did four wrong.
What'd you get for 1?
I don't even know. It's like an absurd amount.
You probably forgot to divide by 100 in the first part. So you probably used 300 instead of 300 equals 100. So you probably forgot to divide by 100. Because I did the same thing and got 185 million.
It was like it was like plus 100.
I don't know. What is it called?
100 was the C constant, and the K constant was something different.
What's it called?
Do we even have to explain how awful that
No, it was E.
Exponential. E to that E over 2.
Oh, sugar plum.
And then you plug in
Girl, what is this? Oh, this is gonna take some time.
Well, the only reason I got number 1 right, or at least I think I got it right, was because I did the practice ones on the computer about 17 times, and it was almost exactly the same.
See, those are the kinds of problems that I didn't understand those.
Thank you.
Are we getting a shark example today? A Sharpie example?
Probably could.
Do we have one shark example per day? No.
I'll do my best to. You guys really are a fun way to end the day, in all honesty. Despite what you think of yourselves, sometimes.
We were early in the day. He's sick of students.
Girl, I think it's sense, you can't convince me otherwise.
Alright, so let's take a look at this picture here, and we'll show it to the folks watching at home on their televisions. So we've got these two objects, and M1 is moving to the right with an original velocity. M2 is moving to the left with an original velocity. There's a cute little spring there. And eventually, they collide, and they compress the spring. Now, at this point, they're both still moving towards each other. So our goal in this problem is to find out two things. Number one, what is the final velocity of the second mass? Because we know the final velocity of the first one. And the other thing we want to know is how far is this spring going to compress?
Really fun.
So do we need to use Hooke's law too?
No, not Hooke's law.
It has to be with pathways, it doesn't have to be horizontal pathways.
What can I say? Let me look up Google. It says before it says
So, in order to start this one, these objects, while they are impacting each other, they are not sticking together. So that means it's still treated as an elastic equation, not inelastic. If they actually did stick together and stuck together, then we would have to treat it differently. So we've still got two separate objects moving at two separate speeds here. So in order to approach this and try and figure out that final velocity, let's just treat it as a regular momentum problem.
It's Robert Hooke. He's the Hooke's law guy. Why is he built like
I seen a
that?
picture of Andy Dalton in high school. Quarterback for the Cowboys.
Oh, I was like, it's not familiar.
So there's your equation. No surprise there. If you want to solve it, you got to isolate V2 and then solve for it, which we'll do.
Every chapter in the new way to say it.
It's kind of what you went over yesterday.
I know. I definitely just elastic.
Yep. So from this, I'm subtracting M1 V1, so I can pull it over there. And then I'm going to divide both sides by M2, and that will get V2 by itself.
Does K go into finding, like, I don't understand where would you plug in K?
Well, we're going to deal with K if
It's separate.
if we use energy, which we're going to do next. So to find V2, we just got to plug all them numbers in.
We'll pretty much be given these numbers, right?
Yeah.
Well, we're going to be given
We're gonna have
like
one big
the
problem.
mass of the objects too. And the original velocity started at 50 meters per second.
You should just give us the mass and the acceleration and tell us to find force.
You guys remember H2O just add water?
It really took me a second, though. Not gonna lie.
This one says
So if you go through and do this, and feel free to check my work here.
You subtract it.
and then
I got negative 1.74.
Oh, I'm not trust your word on that one.
Yes. Yeah, see, people at clubs are just fans of physics.
That's what I was thinking.
They're just saying velocity, velocity,
Wait, what's
velocity.
that supposed to stand for?
This M?
Yeah.
Meters.
No,
I was like, I
the one in
basically.
the denominator.
This
I was
one
like, I
Oh,
basically
yeah,
got
I
the
s-
same answer,
yep,
but it's
this is
double
M2.
that. And I'm like, well, you have to divide by
corresponds to this guy here.
So silly.
I'm so.
Because once we
smart.
move this to the left, we got to divide both sides by M2 to finish getting
I am
velocity
so
2 by
out of
itself.
this. That calc test really wrecked me.
This whole week really reckon.
Questions on this? Good, I'm going to erase it then. And now,
Now he has to plug it in somewhere else.
And now we're only using
Yeah,
one.
now that velocity, you have to plug it into the spring
Wait,
equation.
what was the final answer?
Find out
One negative 1.74. So that mass was moving to the left at 1.74 meters per second. Now we got to figure out how far the spring is going to compress. And the only way we can pull some sort of spring compression distance out of something is using energy.
Wait. Hold on. a second.
Yeah.
How can once they like how can it still be moving this way and this one? Like then they would have to like more go through each other.
We've all been
Well,
there,
it's
right?
the spring isn't fully compressed yet. Like the idea is that you could compress the spring even further.
Okay.
So here, at the beginning, the energy that we have to start is all kinetic because these two objects are moving towards each other. So I'll start with my equation for kinetic energy here. So 1/2 m1 v1 original squared. Same thing for mass 2. And this is going to be kind of a long equation.
Can I ask you kind of a weird question?
No. I wouldn't expect anything less, Placido.
Wait, who was that?
No, it's from you could stop at 5 or 6 stores.
I missed that.
5 or 6 stores or just one? Can I ask you kind of a
I
weird
don't
question?
understand. Oh.
Is it like a movie?
No.
Write that down.
Acting room.
We'll make sense of it if you get lost somewhere in there.
Yeah, I don't know which MV I'm in.
Oh, so you sell for X?
Yeah,
I think there's some.
X marks the spot.
Oh, now we got a little K in there. Same thing,
Yeah. So even though this is a long equation,
Wait,
it's pretty straightforward. This is the kinetic energy at the beginning, because kinetic energy is 1/2 mv squared for mass 1 and mass 2. And then at the end, they're both still moving, so they've both also got final kinetic energy. Plus the spring is compressed, which is where spring compression potential energy comes from. So, to finally solve for x, the first thing I'm going to do is some crossing out. 1/2 is everywhere, so that means we can just get rid of it. Goodbye, 1/2.
But I loved you, what
can you get rid of M? No, they're different. Haha.
Yeah.
Um,
So I'm going to move these two to the left, then divide both sides by k. Yep.
do you like square rooting stuff?
He does?
I had a weird thrill.
Yeah, it just gets me going, you know?
Oh my goodness.
I love making physics.
Sometimes I do too. Sometimes I question myself.
You know what, Katie? I think it's because this room is filled with bottoms.
So this right here is the result of moving this MV and this MV to the other side. And the last thing we need to do is divide both sides by k in order to get that k out of there. And that'll equal x squared. So what's the very, very last thing we got to do? Yeah, square root. So goodbye, square. You're
I
gone.
literally, I was gonna say it, but I was waiting for Seth, and like,
So when we do that, and I'm not going to put the numbers in this one. You guys get the idea.
yeah, whatever.
So when you plug it all in, you'll get a grand total of 0.173 meters for the distance that the spring is compressed.
Wow. Now how do we use that?
How?
We don't. We just
I
That's the kind of knowledge that
I'm guessing you put some.
that's the kind of knowledge you can take with you to the clubs.
why is this?
No.
I suppose this you just go. That would be creepy. Okay, I've got one more example for everybody here. I'll just give you a couple seconds to finish writing if you're still going.
Wait. Let me put on the answer.
When do we get Potter back?
Or never. He's
He's
gone.
not coming back to the second semester.
Ooh.
Because by the time he can come back, he can be one day school.
Yeah.
I mean, it's quarantine for 2 weeks at Point Freckles.
Try to get back.
Write this down, please.
Good try.
Oh, I hate that thing.
Wait,
I'm not writing that down.
That thing makes
You
me-
can't trick me.
That thing makes me angry.
is it shark time?
The summation.
It's pretty much shark time, yes.
Momentum.
Here's the thing about momentum. Just like with energy, it is conserved in every single direction independently. So if you add up all the momentum originally in the x direction, it's going to be equal to the final addition of all the momentum in the x direction. And if you do the same thing in the y direction, all of the starting momentum there will equal all the ending momentum in the y direction. And you'll see an application of this shortly here.
Drawing this makes it easy.
So momentum is conserved in the x and y directions. You don't have to draw this, but I would like you to appreciate how hard I work to make it look nice.
I do appreciate it.
Thank you. So, if you've got two objects here, this one's moving, this one's not. If this eventually impacts this object, you're going to end up with these two objects going in separate directions. This one's going to go up here, this one's going to go down there. And from what we set up here, the overall momentum is conserved in the x and y directions. So, let's just say this object begins with the momentum of like 5 horizontally. That means after the collision, the overall momentum of this object horizontally plus the overall momentum of this object horizontally will be equal to 5. Did I say 5 or 6 before? 5, good, okay. Vertically, obviously, this object is not moving vertically. So the overall vertical momentum of this object up has to be equal to the overall downward momentum that this object has going down. Because momentum has to be conserved. You have to have the same amount up as you do down if you didn't begin with anything vertically. Does that make some sense?
Must be one
I
down.
just, when I saw,
So, oh, go ahead, Sarah.
no, you go.
So, Mr. Hathaway, what you're saying is, this is going to make us better at 8-ball.
That's what I was
That's what I was
saying.
thinking. I was gonna say this
I
reminds
said
me
you
of
must be one
pool.
nasty pool player.
Absolutely. There's so much physics and momentum in pool. So yeah, in red here, this is
We're all
just...
on the same wavelength.
So our final exam is going to be clean.
Can't you get rid of that like middle like desk thing and replace it with the pool table?
I'll sign.
All
Okay.
those who report are on.
You thought about it.
Back here. So this velocity represents the portion of this velocity that's acting horizontally. So it's like adjusted for you. So your horizontal velocity of this object would be its mass times v1 cosine theta. Its vertical velocity is v1 sine theta, and its momentum would be mass times that. So yeah, momentum is conserved in every direction, which is why we can do problems like the one I'm about to put on the board. And this is where the shark's going to come into play.
Yeah!
What kind of shark?
I bet you did not know that this shark can drive.
It looks like
Yeah.
it could. Honestly, it does.
Yeah,
Oh, yeah.
he does. He looks like a mama shark.
Do his arms reach?
So, this shark is driving a car.
Nose.
Oh, I want to see him draw.
I could so picture that.
Oh.
You know, like a seal?
And then instead of, because, you know, it's just one flipper, instead of that, he uses his little, like hand flippers, and then this is, like, go, and this is, like, stop, and then he goes, accept it!
This I feel like this is
No,
gonna be
that's
very
disgusting.
good drivers.
Here we go.
This isn't gonna be good drivers.
This is a shark driver, and this is a penguin driver. I don't like penguins,
Why don't you like
We
penguins?
have a penguin.
because my ex-girlfriend liked penguins.
I hate
So-
that.
True?
All my homies hate penguins.
Yes.
We got you, Mr. Adler.
I appreciate that.
We got you, Mr.
I was
Adler.
like, is that actually true?
It's a,
Yes.
We don't speak of
this is a
penguins.
Penguins don't exist.
So here's what happens.
Seal game.
They make a starfish?
Yes, the shark
This biology class.
and the penguin ram into each other, and they stick together, and they end up going off at an angle. combined. So guess what we're going to do?
Find out
Find the
all
angle.
the stuff.
We are going to find out not only how fast this combination is moving off, but we're going to find out the angle it moved off at.
Oh.
So I'm going to throw in some numbers here, and we'll jump in.
Is there a 9-degree angle for it's easier?
No. Well, no.
Like the angle that they collide at?
Oh, yeah, that's a 90-degree angle. Yep.
What's not a good?
That's a good question.
Yeah, what is it? Oh, okay.
So the penguin, as you can see, is bigger than the shark. It's a fat penguin
No, maybe it's just the car that it's driving.
No,
who
it's
has
a fat
not taken
penguin
care of
fossil.
themselves. So this is what we know. We know the velocities and we know the masses.
It's eating too much of that fish.
Well, I mean, he does live under the water, so maybe he's morphed into some sort of mega penguin that.
No,
Yeah,
he's
keep going.
he's just fat.
Yeah,
So
remember, we don't like penguin kids.
this is what's happening.
Yeah.
And if we want to get started with this, remember that momentum is conserved in the x and y directions. Do we have enough information to find out the momentum in the x and y directions here?
Probably.
Definitely.
Because we've got those values. So let's see what
Like 100%.
we come up with.
I don't know how you would solve for it, honestly. So.
Original momentum in the x direction is going to be equal to m1 and v1 combined.
Oh, okay.
So that comes out to 37,500.
No.
That's a lot.
Kilogram in the y direction. We can do the exact same thing, but with different numbers.
Would
Is
the
it
units of
PY?
acceleration then be
Yes.
Is that PY or PYO?
Oh yeah, PYO.
Stop it.
So that's what we had. When you multiply those together, you're going to get 50,000.
Oh, yeah, that was-
Mr. Happy, please try to say
Kugums.
I said
So we've got these momentums. And now we've got enough information to find out what that angle is.
Okie dokie.
Because we can make this into a triangle.
Wow.
Let me say half angle.
Oh, and then it's 37 and then 50 and then. Got you.
Very good. So, if we want to figure out this angle by using, yeah,
Oh, fancy, fancy.
Okay, well at least this isn't like this.
Came out to be a lot easier than I thought it would be.
Yeah.
right? Opposite over adjacent then, so 50,000 over 37,500. Yep.
Whereas Mr. Mason likes to put on the test. Tangent. That's what the students.
No set.
Come on, Blue, stick with me a bit longer.
I was confused when I saw the text when I was trying to ask what it
This marker's hanging on for dear life.
Is it a geriatric patient?
It's getting there. So when you take the inverse tangent of this, you're going to end up with a beautiful angle of 53.1 degrees.
Oh, I'm in radian mode.
Oh!
Ha, what a loser. Imagine being crazy.
Yeah, imagine being in radian mode.
Hey, at least you didn't know you didn't
Calculator out.
Andrew didn't
That's-
the decrease.
We should have our own physics club, and then dance club. And the only way you get in is if your calculator's in degree mode.
That's if you have to prove that it's
Wait. I'm still not getting the right answer.
password, but I got my calculator degree.
Someone else want to give it a try?
That's what I got.
It's
That's good.
What?
But the thing is, you don't know how to look up it.
I got that answer.
I know, I can't math.
It's okay. So once you get this far, there is one thing we have left to do, and that's solve for this velocity. And it's something that we can actually figure out because, hey, you guys remember back in geometry or whenever you learned the Pythagorean theorem? We can use that here.
Yeah, I know.
So 50,000 squared.
I don't like that.
A squared plus B squared equals C squared. So when you take the square root of all this, you're going to end up with the momentum overall of what the combined masses are as they fly off there. So when you do this math, we'll get
It's the same as vital velocity.
62,500.
I still don't know why.
So this is the overall final momentum of the shark and the penguin, which is in the shark's stomach right now. So
Why actually put it in degrees?
if we know that momentum, we can then, in the end, finally solve for that velocity. Because momentum is just equal to mv. So v then is equal to momentum over mass. So we just do that. And their combined masses, yeah,
Yeah, my degree symbol wasn't working, and I put it actually in degree mode. I got it.
and that'll get us our velocity, 15.6.
Well, I missed a whole bunch.
Hey, where did this one go? Oh, right there.
And that would be our answer.
I got like 12.8.
So once you get
Good afternoon, everybody. We have just a couple of announcements as we close this beautiful day here together at Martin Luther High School. Travel safely home and all this weekend in this beautiful weather. Be smart, drive slowly, and drive carefully. Good luck and do well tonight. All in this weekend, all of our Spartan athletes and co-curriculars that are participating and leading and competing. Do well.